What is up, young chemists? Mr. Rosen here. Today we're going to take some time to talk about molarity in solutions. Molarity is a way to measure the concentration of solutions. So using terms like concentrated or diluted, those are kind of relative terms. Molarity is a more quantitative, number-based way to talk about concentration. So we define the concentration of a solution in terms of the amount of solute dissolved in a given amount of solution. Okay, the solute is the thing that gets dissolved. It's the stuff that you have less of. The solvent is what you put the solute into. The solvent is the thing that does the dissolving. Okay, so the solute goes into the solvent, mix them together, and you get a solution. So those are the two parts of a solution. Now, molarity, which is written as a capital M, is the number of moles of solute per liter of solution. Okay, moles per liter. So molarity is moles per liter. Now, when it comes to solving molarity problems, you usually have two of these three variables. The easiest ones, you're given moles and liters, and you're solving for molarity. But you could be given molarity in liters and solve for moles, or given liters and moles and molarity and solving for liters. Any of the combinations. Okay, now usually you'll see molarity written just as the capital 1, like this means 1 molar solution. 1 molar solution means 1 mole of solute is dissolved in every liter of solution. So I'm going to do a variety of molarity problems, maybe solving for different variables, or you'll see some different types or styles. The most straightforward kind, they give you moles and they give you liters, and that's it. In this example problem, it says, what's the concentration? Unfortunately, that's an immediate typo. It says, what is the concentration of a solution, sorry about that, that contains 0.08 moles of sodium sulfate in 42.0 milliliters of solution. So in terms of solving this, you need to figure out what do we know and what are we trying to find, what do we not know. So in terms of variables, we have 0.0800 moles, okay? They're asking for concentration. So if they're asking for concentration, you're solving for molarity. Molarity equals moles over liters, right? But we actually don't have liters. We have milliliters. So that's not going to work. We can't solve as is. So we actually have to convert our milliliters into liters. And there are 1,000 milliliters in 1 liter. So to convert, you say 42.0 milliliters. 1 liter is 1,000 milliliters. Okay, we're dividing by 1,000 here. It's the same as moving the decimal 3 places to the left. We get 0.042 liters. So now we have everything that we need to solve for molarity. So molarity is moles divided by liters. So molarity is going to be 0.0800 moles divided by 0.0420 liters. And we'll get our molarity. Okay, so 0.08 divided by 0.042, and we're going to go to 3 significant figures on that, so that's 1.90 molarity, which is our answer. That means that 1.9 moles are dissolved per liter of solution. Now, we're going to do a couple of problems where we have to solve for different things in different ways. So in that case, that last problem, you were given moles and you had milliliters, and we had to convert milliliters. But in this problem, it says, what's the concentration of a solution that contains 138 grams of sodium hydroxide in 3.2 liters? So in this case, we do have liters, which is nice. We don't have to convert that, but we have grams. Okay, molarity is moles per liter, right? Molarity is moles per liter. So we need to convert 138 grams of NaOH. We need to turn that into moles. So 1 mole of NaOH, we have to add that up and find its molar mass. Sodium is 22.99, so we say 22.99 plus oxygen is 16 plus hydrogen 1.01. We get 40 grams per mole. So if we take 138 and divide it by our molar mass, we get 3.45 moles. And now we're actually ready to do some solving here because remember, molarity is moles per liter. We now have moles and we already have liters. So moles divided by liters gives us the molarity. So if I take this and I divide by 3.2, I get my molarity, which is about 1.08. That's moles per liter. All right, so that's one style. It's a little different. We had to turn grams into moles first. Last problem, we had to turn milliliters into liters. So it's pretty regular or pretty common that you have to convert something into something else. Question number 2 says, how many grams of HCl are needed to make 4.5 liters of 2.6 molarity solution? So this one you might say, hold on a second, to actually give you the molarity. Okay, now it might be helpful. Some students like drawing, a triangle like this to help solve, where, break this up, you say molarity is moles over liters, right? And these are being multiplied. So molarity is moles divided by liters. Volume in liters is moles divided by molarity. And moles is molarity times liters. So you're always going to end up with 2 of those 3 and solve for the other. This says how many grams of HCl are needed to make 4.5 liters. So we have volume in liters, and we have molarity. So we have volume and molarity. We have these 2 right here. If we multiply molarity and volume, we get moles, right? Because 2.6 molarity is the same as moles per liter. That's moles per liter. And we have 4.5 liters. So if you take molarity times liters, liters is going to cancel out, and you're going to be left with your number of moles. So 2.6 times 4.5 is 11.7 moles of HCl. So 11.7 moles of HCl are needed. But the question doesn't ask how many moles of HCl, it asks how many grams. So we need to take 11.7 moles of HCl and convert it into grams of HCl. So if we're trying to find grams, we put grams on top, 1 mole of HCl on bottom. So we have to put the molar mass of HCl. Chlorine is 35.45. Hydrogen is 1.01. So if we add those together, we get 36.46 grams per mole. So I'm just going to take this number times 36.46. And we get our answer. This is now in grams for 27 grams of HCl. And that's our number of grams. Number 3 says, what volume of 2.45 molarity KCl could be made by dissolving 233 grams. I screwed this up again, sorry. MgCl2. I tried to change this from other practice problems, so I apologize about that. It says, what volume of 2.45 molarity magnesium chloride could be made by dissolving 223 grams of magnesium chloride into solution? So in this problem, you're given molarity and you're given grams. And we're solving for volume in this case. So you're going to need to take the grams of MgCl2 and you're going to need to turn them into moles. So 223 grams of MgCl2, turn them into moles. 1 mole of MgCl2 is some number of grams. So we'll add that up. Chlorine is 35.45 and we have 2 of them. And then magnesium is 24.31. So our molar mass is 95.21 grams per mole. If we take 223 and we divide it by that number, we get 2.34 moles of MgCl2. So now we have moles and we have molarity. Okay, going back to our little handy dandy triangle here, if we have moles and molarity, we can solve for volume, right? Moles divided by molarity is liters. So if I take my moles and I divide it by the molarity, which is 2.45 molarity, moles will cancel in terms of units and we'll be left with our volume in liters. So divide that by this, and we get 0.956 liters as our volume. So, the idea here is you might be given grams and you have to turn it into moles, and then you have 2 of the 3 variables. Or you might be given moles and you end up solving for grams and you have to convert to grams. But either way, you end up with 2 of the 3 here and you solve for the one you don't know. And you might need to convert into or out of moles to or from grams. Now, we are going to do one other style of molarity problem here today, and that is what's called a molarity by dilution problem. Molarity by dilution problems, as we have it written here, it's when you just have, molarity by dilution here, we have it written as M1V1 equals M2V2. It's very, very similar to Boyle's law, except for instead of pressure, you have molarities. And if you have a solution with known concentration and volume, and you're going to dilute it, you can easily find what the ending concentration is going to be. And the reason is, if you take molarity times volume, as we saw in our triangle recently, molarity times volume is moles. So if you have an original solution and you're diluting it, when you're diluting it, you're not adding anything but water to it. So this is moles of solute, and after you dilute it, you still have the same number of moles of solute, right? That's not changing when you dilute it. So even though the volume, if let's say you dilute it and the volume goes up, that means the molarity is going to go down. If one goes up, the other goes down. But the number of moles of solute stays the same when you dilute it because you're just adding water to it. All right, so the M's are molarity and the V's are volume of solution, and the 1's are starting conditions and the 2's are ending conditions. So an example problem says that I have to prepare a lab activity and it requires 2.5 liters of 1.75 molarity HCl. The stock solution, which is the more concentrated solution that I make it from, is 12 molarity. So the question is asking, what volume must Mr. Rosen dilute in order to make 2.5 liters of the solution that I want, right? So the starting molarity is 12 molar HCl. I'm trying to figure out what amount of it I need to dilute in order to have an ending molarity of 1.750 and an ending volume of 2.5 liters, right? So I know what volume of what molarity I want to end up with, and I know the starting molarity. I'm wondering, what volume do I need to dilute? All right, so I'm going to plug each of these into the equation. So 12 molarity is my starting molarity. V1 is what I'm solving for. My ending molarity is 1.75, and my ending volume is 2.5 liters. So to solve for V1, I'm going to get V1 all by itself on one side of the equal sign. Whatever I do to one side, I do to the other. If I do this, units of molarity will cancel, and I'll be left with my answer in liters. So 1.75 times 2.5 divided by 12, I get 0.364 liters as my original volume. So what that means is if I have 0.364 liters of the stock solution, I can add water to it until my ending volume is 2.5 liters. And if I do that, then the molarity is going to be what we're looking for, 1.75. All right, so notice here that the volume increases and the molarity decreases. And this just says isolate the variable, which is what we did, and then we arrive at our answer. We'll do a couple of examples real quick. So number one says if 0.95 liters of 15 molarity ammonium hydroxide is diluted to a volume of 3.25 liters, what will be the new molarity of the solution? So new molarity is M2. So M1V1, right, M1V1 equals M2V2. So our starting molarity is 15. Our starting volume is 0.950 liters. Ending molarity is what we're solving for, and our ending volume is 3.25 liters. Now, before we even solve, we should think about how this is going to change, right? The volume goes from 0.95 to 3.25, so the volume is increasing, which means we're taking this and we're watering it down, okay? In fact, the volume is more than 3 times larger than we started with, which means our molarity is going to be less than a third of what we started with. We'd expect it to be less than 5, 4 point something probably. Now let's actually solve. We're going to divide by 3.25 liters so that it cancels. Whatever we do to one side, we do to the other, 3.25 liters. Okay, units of liters will cancel, and we will get our ending molarity, which here, let's do this, 15 times 0.95 gives us some number divided by 3.25. We get 4.38. That's our molarity. And like I said, it's like we expected. The volume more than tripled, so our molarity is going to be less than a third. All right. Question number 2. It says, to how much water should 150 milliliters of 12 molarity hydrochloric acid be added to produce a 6 molarity solution? So we have 2 molarities and we have 1 volume. So 12 molarity times 150 milliliters. Okay, now the math will work here if you leave it in milliliters. You could get in the habit of converting to liters, but it doesn't really matter in this case. Actually, let's just convert this. This is it's better to just convert this here. Okay, this is in liters. Just get in the habit of converting to liters. And then this is molarity, and we're solving for V2. Now, the thing is, just solving for V2 is actually not going to get us our answer. We're going to divide by 6 molarity on this side. That cancels. We divide by 6 molarity on this side. Now, you might even think, okay, we're starting at 12 and we're ending up at 6. So if the molarity is getting split in half, that means that the volume is going to double, right? And, of course, we could plug that in here. 12 times 0.15 is some number divided by 6.3, right? That is 0.3 liters. That's our ending volume, which makes sense, right? 0.3 liters is twice what we started at. Okay, now the question actually asks, to how much water should 150 milliliters be added to end up with this? So that means our ending volume needs to be 3 liters. But of that 3 liters, 150 of it is the original acid. So we actually need to add 150 milliliters to 150 milliliters in order to get this, which is the same as 300 milliliters, right? So when it says, you could take this and subtract this, right? But I just sort of, in my head, can see that 150 milliliters plus 150 milliliters gives you 300 milliliters. So when it says, to how much water should this be added, 150 milliliters of acid needs to be added to 150 milliliters of H2O in order to arrive at that volume. So this is your answer. So it's a little bit of a different wrinkle on the same style of problem. So today we've done a whole bunch of different problems related to molarity, right? Molarity, which is measure of concentration, moles per liter. We also did some molarity by dilution problems. You're usually going to have, in the case of molarity, 2 of the 3 variables and you solve for the other. Sometimes you have to convert 2 grams from moles or from moles to grams, but they're all pretty similar. Hopefully this has been helpful. Work, 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 study, study, study.